Welcome to The Sleepless Universe. In this video, we're diving into some of the strangest and most fascinating paradoxes in the universe. If you enjoy this kind of content, I'd really appreciate it if you gave this video a like and subscribed to our channel. Feel free to drop a comment telling me where you're watching from and what time it is for you right now. Now, sit back, relax, and enjoy the journey. Olbers Paradox. When you look up at the night sky, you see a tapestry of darkness punctuated by points of light. This simple observation holds within it one of astronomy's most elegant puzzles, known as Olbers Paradox. Named after the German astronomer Heinrich Olbers, this paradox asks a deceptively simple question. If the universe contains an infinite number of stars distributed throughout infinite space, why isn't every direction in the sky blazing with starlight? The logic seems straightforward. Imagine looking through a forest where trees are randomly scattered. If the forest is large enough and dense enough, no matter which direction you look, your line of sight will eventually encounter a tree trunk. Similarly, if space contains an infinite number of stars, every direction should lead your gaze to a star's surface. The night sky should be as bright as the surface of the sun itself, a continuous dome of brilliant light. Yet when we step outside on a clear night, we encounter profound darkness between the stars. This darkness is so fundamental to our experience that we rarely question it, but it represents a deep mystery about the nature of our universe. The resolution to Olbers' paradox lies in understanding the universe's finite age and the finite speed of light. Our universe began approximately 13.8 billion years ago, which means light from distant stars has had only a limited time to reach us. Many stars are so far away that their light simply hasn't had enough time to travel across the vast cosmic distances to arrive at Earth. Additionally, the universe is expanding, stretching the space between galaxies and causing light from distant objects to become redshifted. This expansion means that light from the most distant regions becomes shifted toward longer, redder wavelengths, eventually moving beyond the visible spectrum entirely. The finite age of stars themselves also contributes to the solution. Stars are not eternal beacons burning since the beginning of time. They form, live, and die according to cosmic timescales. Many regions of space contain no stars at all, while others harbor stellar nurseries where new stars are just beginning to ignite. Interstellar dust and gas provide another piece of the puzzle. These cosmic materials absorb and scatter starlight, creating dark lanes and regions that block our view of more distant stars. The universe is not the transparent, empty space that early astronomers imagined, but rather a complex medium filled with matter that can obscure and redirect light. The cosmic microwave background radiation, the afterglow of the Big Bang, represents the most distant light we can observe. This faint radiation fills all of space, but it has been stretched by cosmic expansion to microwave wavelengths, far beyond what our eyes can detect. The paradox also reveals something profound about the structure of matter itself. In an infinite universe filled with infinite stars, the gravitational effects would be equally paradoxical. The night sky's darkness suggests that our universe has boundaries in time, even if not in space. Modern observations of distant supernovae and galaxy redshifts have confirmed that the universe is not only expanding, but accelerating in its expansion. This acceleration, driven by mysterious dark energy, further ensures that light from the most distant regions becomes increasingly redshifted and dim. Olbers' paradox beautifully illustrates how a simple observation about darkness can reveal fundamental truths about cosmic evolution, the finite speed of light, and the dynamic nature of our expanding universe. The darkness between stars is not empty space, but rather a window into the universe's history and structure, telling us that we live in a young, expanding cosmos, where light has not yet had time to fill every corner of the night sky. Fermi Paradox. The vastness of space stretches beyond human comprehension, containing hundreds of billions of galaxies, each hosting countless stars and planetary systems. Within this cosmic immensity, the mathematical probability suggests that intelligent life should be abundant throughout the universe. Yet, when we listen to the cosmos with our most sensitive instruments and scan the heavens with our most powerful telescopes, we encounter a profound silence. This contradiction between expectation and observation forms the heart of the Fermi Paradox. named after physicist Enrico Fermi, who famously asked, "Where is everybody?" during a casual lunch conversation in 1950. This paradox challenges our assumptions about life in the universe. The numbers seem compelling. Our galaxy alone contains over 100 billion stars, many of which host rocky planets in habitable zones where liquid water could exist. If even a tiny fraction of these worlds developed intelligent life, the galaxy should be teeming with civilizations. The Drake equation, formulated by astronomer Frank Drake, attempts to quantify the likelihood of communicating extraterrestrial civilizations. While its variables remain largely unknown, even conservative estimates suggest that numerous intelligent species should exist within our cosmic neighborhood. These civilizations, given enough time, might develop technologies for interstellar communication or travel, making their presence detectable across vast distances. Several explanations have been proposed for this cosmic silence. The Great Filter hypothesis suggests that there exists some evolutionary step so difficult that it prevents most life from reaching technological sophistication. This filter might lie in our past, explaining why we seem alone, or in our future, representing a challenge we have yet to face. Perhaps intelligent civilizations consistently destroy themselves through warfare, environmental collapse, or other catastrophes before achieving interstellar capabilities. The brief span of human technological development, measured in mere centuries against cosmic timescales, might represent a typical pattern where civilizations rise and fall too quickly to make contact. Another possibility involves the sheer scale of space and time. Even if numerous civilizations exist, the vast distances between stars and the finite speed of light might make contact extraordinarily rare. Civilizations might rise and fall while their signals are still traveling through the cosmic void, like ships passing in an infinite night. Some scientists propose that advanced civilizations might deliberately remain hidden, following something like a cosmic version of the Prime Directive from science fiction. They might observe younger civilizations without interfering, waiting for them to reach certain developmental milestones before making contact. The search continues through projects like SETI, scanning radio frequencies for artificial signals, and through the discovery of exoplanets in habitable zones around distant stars. Each new world we find both increases the potential for life and deepens the mystery of silence. Recent discoveries have revealed thousands of potentially habitable worlds throughout our galaxy. The Kepler Space Telescope and other instruments have shown that rocky planets in the habitable zones of their stars are remarkably common. This makes the silence even more profound, as the conditions for life appear to be widespread throughout the cosmos. Perhaps the most unsettling possibility is that we are among the first intelligent species to emerge in our galaxy. The universe is young compared to the potential lifespan of stars, and complex life may require billions of years to evolve. We might be cosmic pioneers, destined to encounter the silence not because life is rare, but because we are among the early arrivals to the cosmic stage. The Fermi Paradox reminds us that despite our growing understanding of the universe, fundamental questions about our place in the cosmos remain unanswered. Whether we are alone, rare, or simply looking in the wrong places, the silence of space continues to challenge our understanding of life's place in the infinite expanse of existence. Horizon Problem. Deep space holds secrets written in ancient light, and one of the most puzzling messages comes from the cosmic microwave background radiation. This faint glow, the afterglow of the Big Bang itself, fills every corner of the observable universe with remarkable uniformity. When astronomers measure its temperature, they find it varies by less than 1 part in 100,000 across the entire sky. This extraordinary uniformity presents what cosmologists call the horizon problem. The puzzle lies in understanding how regions of space that should never have been in contact with each other came to have nearly identical temperatures. In the early universe, light had only limited time to travel between distant regions. The cosmic horizon represents the maximum distance light could have traveled since the Big Bang, defining the boundary of what different regions could have influenced each other. Consider two opposite regions of the sky, separated by an angle of 180 degrees as seen from Earth. The light from these regions has traveled for nearly 14 billion years to reach us, coming from opposite directions across the observable universe. According to standard Big Bang cosmology, These regions were never close enough for light to travel between them, meaning they should have evolved independently with no mechanism to synchronize their temperatures. Yet, when we measure the cosmic microwave background from these widely separated regions, we find their temperatures are identical to extraordinary precision. It's as if two isolated rooms with no connection between them somehow maintained exactly the same temperature without any means of heat exchange. The uniformity extends beyond just temperature. The density of matter and energy in the early universe shows the same remarkable consistency across regions that should have been causally disconnected. This suggests that the entire observable universe somehow reached thermal equilibrium, despite the apparent impossibility of communication between distant regions. The leading solution to the horizon problem comes from cosmic inflation theory. This proposes that in the universe's first fraction of a second, space underwent a period of exponential expansion, stretching faster than the speed of light. During this inflationary epoch, regions that are now separated by billions of light years were once close enough to exchange energy and reach thermal equilibrium. Inflation suggests that our entire observable universe began as a tiny, causally connected region smaller than an atomic nucleus. This minuscule region contained the seeds of everything we can see today. As inflation stretched this region to cosmic proportions, it preserved the thermal equilibrium that had been established when everything was in close contact. The mechanism works like stretching a small, uniformly heated piece of material to enormous size. The temperature remains uniform across the expanded material because every part originated from the same small, equilibrated region. Similarly, cosmic inflation stretched a tiny, uniform patch of space-time to become our observable universe. This solution also explains why the universe appears so flat on large scales, and why exotic relics from the early universe, such as magnetic monopoles, are not observed today. Inflation would have diluted these relics to undetectable levels while preserving the thermal equilibrium established in the pre-inflationary era. The precision measurements of the cosmic microwave background by satellites like Planck have confirmed inflation's predictions with remarkable accuracy. The tiny temperature fluctuations we observe correspond to quantum fluctuations from the inflationary epoch, stretched to cosmic scales and preserved as the seeds of all cosmic structure. The horizon problem beautifully illustrates how observations of ancient light can reveal the universe's most fundamental properties. The uniformity of the cosmic microwave background serves as evidence for one of the most dramatic events in cosmic history, when space itself expanded faster than light could travel, connecting regions that would otherwise remain forever isolated in the cosmic dark. Flatness problem. The geometry of space itself holds profound mysteries that challenge our understanding of cosmic evolution. When cosmologists measure the overall shape of our universe, they discover something remarkable and puzzling. Space appears to be almost perfectly flat. This geometric precision presents what scientists call the flatness problem, one of the most elegant puzzles in modern cosmology. To understand this problem, imagine the universe as a vast surface that could curve in different ways. Like a sphere that curves inward or a saddle that curves outward, space-time itself can have positive, negative, or zero curvature. A flat universe has zero curvature, meaning that parallel lines remain parallel forever, and the angles of triangles always sum to exactly 180 degrees, just as they do on a flat sheet of paper. The mystery lies not in flatness itself, but in its incredible improbability. The curvature of space depends on a delicate balance between the universe's total energy density and a critical value that marks the boundary between different geometric possibilities. If the actual density is even slightly higher than this critical value, space curves inward like a sphere and eventually collapses back on itself. If the density is slightly lower, space curves outward like a saddle and expands forever at an accelerating rate. What makes this remarkable is the precision required. For the universe to remain nearly flat for billions of years, its initial density must have been extraordinarily close to the critical value. The required accuracy is similar to balancing a pencil on its point, theoretically possible, but requiring such precise initial conditions that random chance seems an inadequate explanation. As the universe evolves, any deviation from perfect flatness grows larger over time. A universe that begins slightly curved becomes increasingly curved as it ages. For our universe to appear flat today, after nearly 14 billion years of evolution, it must have started with a density that matched the critical value to more than 50 decimal places. This level of precision appears far too unlikely to result from random initial conditions. It's as if someone carefully tuned the universe's density dial to an extraordinarily specific setting, suggesting that some mechanism must have driven the universe toward flatness rather than leaving it to chance. Cosmic inflation theory provides an elegant solution to the flatness problem. During the inflationary epoch, space expanded exponentially, stretching any initial curvature to enormous scales. Just as the surface of a balloon appears increasingly flat as the balloon expands, cosmic inflation stretched space so dramatically that any original curvature became imperceptible. This expansion occurred so rapidly and extensively that even if the universe began with significant curvature, inflation would have flattened it to the precision we observe today. The mechanism works automatically, requiring no fine-tuning of initial conditions. Any curved space, when stretched sufficiently, appears flat to observers within it. The flatness problem illustrates how the universe's large-scale geometry connects to its earliest moments. The nearly perfect flatness we measure today serves as a fossil record of cosmic inflation, preserving evidence of the universe's most dramatic period of growth in the precision of spacetime's geometry. Cosmological constant paradox. Deep within the fabric of spacetime lies one of physics' most perplexing mysteries. Empty space itself appears to possess energy, a property that drives the accelerating expansion of our universe. This energy, known as dark energy, manifests through what Einstein called the cosmological constant. Yet when physicists attempt to calculate this constant's value from fundamental principles, they encounter a discrepancy so enormous it defies comprehension. The cosmological constant paradox. The story begins with quantum field theory, our most successful description of the microscopic world. According to this theory, empty space is never truly empty. Instead, it seethes with virtual particles that constantly pop into existence and annihilate in fleeting moments. These quantum fluctuations should contribute energy to the vacuum itself, creating what physicists call vacuum energy density. When scientists calculate how much energy these quantum fluctuations should contribute to empty space, they arrive at a number that is almost incomprehensibly large. This theoretical prediction suggests that the vacuum energy density should be so enormous that it would cause the universe to expand at a rate trillions upon trillions of times faster than what we observe. Yet when astronomers measure the actual rate of cosmic expansion, they find that dark energy contributes a much more modest amount. The observed value of the cosmological constant is approximately 120 orders of magnitude smaller than quantum field theory predicts. This represents the largest discrepancy between theory and observation in all of science. To put this difference in perspective, imagine predicting that a feather should weigh as much as all the atoms in the observable universe, only to find that it weighs exactly what a feather should weigh. The mismatch between prediction and reality is so vast that it challenges our understanding of both quantum mechanics and gravity. The paradox deepens when we consider that the cosmological constant must be precisely the value we observe for the universe to evolve as it has. If dark energy were much larger, cosmic expansion would have been so rapid that galaxies, stars, and planets could never have formed. If it were much smaller or negative, the universe might have collapsed before complex structures could develop. This fine-tuning puzzle suggests that either our understanding of quantum field theory is fundamentally incomplete, or some unknown mechanism precisely cancels most of the vacuum energy. Some theories propose that additional fields or symmetries might reduce the effective cosmological constant to its observed value, but no convincing mechanism has been found. String theory and other advanced frameworks attempt to address this paradox by suggesting that our universe might be one of many in a vast multiverse. In this scenario, different regions might have different values of the cosmological constant, and we naturally find ourselves in a region where the value allows for the formation of complexity and life. The cosmological constant paradox represents more than just a numerical puzzle. It suggests that our understanding of the deepest levels of reality remains incomplete. The vast empty spaces between galaxies, rather than being simple voids, may hold the key to understanding how quantum mechanics and gravity unite in the cosmic dance of existence. Baryon Asymmetry Paradox. In the deepest foundations of reality lies a profound imbalance that makes our existence possible. The universe we inhabit is built almost entirely from matter. The protons and neutrons that form atomic nuclei, the electrons that orbit them, and all the complex structures they create. Yet according to our understanding of fundamental physics, the Big Bang should have produced equal amounts of matter and antimatter, particles that annihilate each other upon contact and leave behind only pure energy. This presents the Baryon Asymmetry Paradox, one of cosmology's most fundamental puzzles. For every proton in the universe today, there should be an antiproton. For every electron, a positron. When these particle pairs meet, they destroy each other completely, converting their mass into photons of light according to Einstein's famous equation relating mass and energy. If the early universe began with perfect symmetry between matter and antimatter, the two should have annihilated completely, leaving behind a cosmos filled only with photons and other massless particles. There would be no atoms, no stars, no planets, and certainly no observers to contemplate this cosmic emptiness. Yet, here we are, surrounded by matter-dominated galaxies, evidence of a fundamental asymmetry written into the fabric of existence itself. Current observations suggest that for every billion antimatter particles in the early universe, there were approximately 1,000,000,001 matter particles. This tiny excess, just 1 part in a billion, survived the Great Annihilation and went on to form everything we see today. The cosmic microwave background radiation that fills space represents the afterglow of this primordial annihilation event, while the matter around us descended from the minute surplus that remained. The mystery deepens when we consider that all known physical laws appear to treat matter and antimatter symmetrically. For every process that creates a matter particle, there should be a corresponding process that creates an antimatter particle. This fundamental symmetry, called charge conjugation parity, suggests that the universe should maintain equal amounts of both throughout its evolution. However, scientists have discovered subtle violations of this symmetry in certain particle interactions. These violations are extraordinarily small, much smaller than what would be needed to explain the observed matter dominance. The known asymmetries can account for only a tiny fraction of the matter surplus we observe, leaving the vast majority of the imbalance unexplained. Some theories propose that additional sources of asymmetry existed in the very early universe, perhaps during phase transitions, when the fundamental forces separated from their unified state. These mechanisms might have preferentially produced matter over antimatter during brief moments when the universe was hot and dense enough for such exotic processes to occur. Another possibility involves the existence of additional particles or forces beyond our current standard model of physics. These hypothetical components might interact differently with matter and antimatter, creating the observed imbalance through mechanisms we have yet to discover or understand. The search for antimatter in the cosmos continues through space-based detectors and particle accelerators. Each antiparticle detected in cosmic rays provides clues about the universe's fundamental asymmetry, while laboratory experiments probe the subtle differences between matter and antimatter behavior. The Baryon Asymmetry Paradox reminds us that our very existence depends on a cosmic imbalance we do not yet fully understand. The stars that light the night sky, the planets that orbit them, and the life that flourishes in rare corners of the universe all exist because of a mysterious preference for matter over antimatter encoded in the universe's earliest moments. Black hole information and paradox. Black holes represent the most extreme environments in the universe, regions where gravity becomes so intense that not even light can escape their grasp. These cosmic phenomena challenge our understanding of physics in profound ways, but perhaps no puzzle is more perplexing than the black hole information paradox, a problem that strikes at the heart of how information itself behaves in our universe. The paradox emerges from the collision between two fundamental principles of modern physics. Quantum mechanics tells us that information cannot be destroyed. It can be scrambled, hidden, or transformed, but it must always be preserved in some form. This principle ensures that the universe maintains a consistent account of all quantum states and their evolution through time. General relativity, however, suggests that when matter falls into a black hole, it disappears forever beyond the event horizon, the boundary from which nothing can return. As the black hole eventually evaporates through Hawking radiation, a quantum process that slowly converts the black hole's mass into thermal energy, all trace of the original matter seems to vanish completely. Stephen Hawking's groundbreaking work revealed that black holes emit radiation due to quantum effects near the event horizon. Virtual particle pairs constantly appear and separate near this boundary, with one particle falling into the black hole, while the other escapes as radiation. This process gradually reduces the black hole's mass, causing it to shrink and eventually disappear entirely. The paradox lies in the nature of this Hawking radiation. It appears to be perfectly thermal, carrying no information about the matter that originally formed the black hole. Whether the black hole formed from collapsed stars, planets, books, or computers, the outgoing radiation seems identical in all cases. This suggests that vast amounts of information simply vanish when black holes evaporate, violating the fundamental principle of information conservation. The implications extend far beyond black holes themselves. If information can be destroyed in these extreme environments, it calls into question the consistency of quantum mechanics and our understanding of how the universe maintains its coherent structure. The loss of information would represent a fundamental breakdown in the predictable evolution of physical systems. Several potential solutions have been proposed to resolve this paradox. Some suggest that information is preserved but encoded in subtle correlations within the Hawking radiation, scrambled in ways so complex that it appears random to current detection methods. The information might be recoverable in principle, though the process would require impossibly precise measurements of the radiation's quantum state. Other theories propose that the information never actually crosses the event horizon from the perspective of outside observers. Instead, it remains encoded on the black hole's surface, stretched and redshifted by extreme gravitational effects, but never truly lost. This approach suggests that the event horizon acts more like a holographic screen than an absolute boundary. More radical solutions involve modifications to our understanding of space-time itself. Some physicists propose that black holes create bridges to other regions of space-time, allowing information to escape through hidden channels. Others suggest that the smooth space-time near black holes is an illusion, replaced by a more fundamental structure that preserves information through mechanisms we have yet to discover: the black hole. Information paradox continues to drive research at the frontier of theoretical physics, where quantum mechanics meets gravity in the most extreme conditions imaginable. Its resolution may require a complete revolution in our understanding of space, time, and information itself. Arrow of time. Paradox. Time flows in one direction through our everyday experience, carrying us from past through present toward an uncertain future. This arrow of time seems so fundamental to existence that we rarely question its nature, yet it presents one of physics' most subtle and profound paradoxes. The equations that govern the microscopic world show no preference for any particular direction of time, yet the macroscopic universe exhibits a clear and unwavering temporal asymmetry. Consider the fundamental laws of physics that describe how particles interact and evolve. Whether we examine Newton's laws of motion, Maxwell's equations for electromagnetism, or the Schrödinger equation of quantum mechanics, these mathematical descriptions remain essentially unchanged when time runs backward instead of forward. A collision between two particles looks equally valid whether viewed as a movie running forward or in reverse. Yet our macroscopic world tells a different story entirely. We remember the past, but not the future. Eggs fall and break, but never spontaneously reassemble. Heat flows from hot objects to cold ones, but never the reverse without external work. Stars burn their nuclear fuel and eventually die, never spontaneously igniting from cold gas clouds. These processes define a clear direction for time's passage. The resolution to this paradox lies in the concept of entropy, a measure of disorder or randomness in physical systems. The second law of thermodynamics states that entropy always increases in isolated systems, providing the universe with its temporal direction. This law emerges from statistical mechanics. While individual particles follow time-symmetric rules, large collections of particles overwhelmingly evolve toward more probable, higher entropy states. Imagine a box containing gas molecules all crowded into one corner. While the microscopic laws permit these molecules to remain clustered together, the probability of this occurring decreases exponentially with the number of particles involved. The molecules will almost certainly spread throughout the box, increasing the system's entropy and defining a clear arrow of time. The puzzle deepens when we consider the universe's origin. For entropy to increase consistently throughout cosmic history, the universe must have begun in an extraordinarily low entropy state. The early universe was remarkably smooth and uniform, far from the maximum entropy configuration we might expect from random initial conditions. This initial condition represents a profound fine-tuning problem. Among all possible ways the universe could have begun, only an infinitesimally small fraction would lead to the low entropy start required for time's arrow. The probability of randomly achieving such initial conditions is so small that it approaches zero for all practical purposes. Cosmic inflation provides one potential explanation for this low entropy beginning. During the inflationary epoch, space expanded exponentially, stretching any initial irregularities to enormous scales and leaving behind a smooth, uniform distribution of matter and energy. This process could naturally generate the low entropy initial state required for the arrow of time. Some physicists propose that time's arrow is not fundamental but emergent, arising from our particular perspective within the universe. In this view, there exist regions of space-time where entropy decreases, creating local arrows of time pointing in different directions. We naturally find ourselves in a region where entropy increases in the direction we call future. The relationship between consciousness and time's arrow adds another layer of mystery. Our perception of temporal flow might be intimately connected to the thermodynamic processes in our brains, which themselves follow the universal increase in entropy. The arrow of time. Paradox illuminates the deep connection between the universe's microscopic foundations and its macroscopic behavior, revealing how statistical principles can create asymmetry from fundamentally symmetric laws. Boltzmann Brain Paradox. Deep within the realm of statistical mechanics lies a thought experiment so strange and unsettling that it challenges our most basic assumptions about reality and consciousness. The Boltzmann Brain Paradox, named after physicist Ludwig Boltzmann, explores the possibility that, in an infinite or sufficiently long-lived universe, random thermal fluctuations could spontaneously create a functioning brain, complete with false memories and consciousness. The paradox begins with a simple observation about entropy and probability. In any system with finite energy, thermal fluctuations constantly occur, causing particles to move and arrange themselves in countless different configurations. While most arrangements are highly disordered, occasionally random motion will create pockets of lower entropy and greater organization. Given enough time and space, these fluctuations could theoretically assemble any possible structure, no matter how complex or improbable. Just as a group of monkeys randomly typing might eventually produce Shakespeare's complete works, thermal fluctuations might randomly arrange atoms into a human brain, complete with all the neural connections necessary for consciousness and memory. Such a spontaneously formed brain would possess the illusion of a complete life history, false memories of experiences it never had, and the conviction that it exists within a larger universe filled with stars, planets, and other people. From the brain's perspective, its reality would be indistinguishable from our own, even though it formed through pure chance in an otherwise empty void. The disturbing implication is that, in an infinite universe, there should be vastly more Boltzmann brains than naturally evolved brains like our own. The probability of forming a single brain through random fluctuation, while incredibly small, is far larger than the probability of evolving an entire civilization through natural selection and cosmic evolution. This leads to an unsettling conclusion. If we find ourselves conscious and observing the universe, it is statistically more likely that we are spontaneously formed Boltzmann brains with false memories rather than naturally evolved humans living in a real cosmos. Our entire perception of reality, including our scientific understanding and observations of distant galaxies, would be nothing more than random neural activity in an isolated brain floating in empty space. The paradox becomes even more troublesome when applied to cosmological models. In theories where the universe expands forever and maintains a finite temperature, thermal fluctuations will continue indefinitely. Over infinite time, these fluctuations will produce an infinite number of Boltzmann brains, each convinced of its own elaborate false history. Some solutions to the paradox involve modifying our understanding of cosmology itself. If the universe has a finite lifetime, or if dark energy eventually causes space to expand so rapidly that thermal fluctuations become impossible, then Boltzmann brains might never form. The observed acceleration of cosmic expansion could serve as a natural cutoff, preventing these random consciousness formations. Other approaches question the assumption that consciousness can emerge from arbitrary neural arrangements. Perhaps genuine consciousness requires specific historical processes or environmental interactions that cannot be replicated through random assembly. The complex chemistry of life and the intricate development of nervous systems might be prerequisites for true awareness. The paradox also highlights the importance of anthropic reasoning in cosmology. When evaluating cosmological models, we must consider not just whether they allow observers to exist, but whether they predict that most observers are naturally evolved rather than randomly assembled. The Boltzmann brain paradox forces us to confront fundamental questions about consciousness, reality, and our place in the cosmos, reminding us that even our most confident assumptions about existence may rest on surprisingly shaky statistical foundations. Hubble tension paradox. The universe expands at a rate that should be precisely measurable, yet modern astronomy faces a perplexing problem. Different methods for determining this expansion rate yield conflicting results. This discrepancy, known as the Hubble tension, represents one of the most significant challenges in contemporary cosmology, suggesting that our understanding of cosmic evolution may be fundamentally incomplete. The Hubble constant describes how quickly space itself stretches, determining how fast distant galaxies recede from us due to cosmic expansion. This single number encodes crucial information about the universe's age, composition, and ultimate fate. Its precise measurement should provide a cornerstone for our cosmic model, yet recent observations have revealed a troubling inconsistency. One approach measures the expansion rate using observations of the cosmic microwave background radiation, the ancient light that filled the universe when it first became transparent. Satellites like Planck have mapped this radiation with extraordinary precision, revealing tiny temperature fluctuations that encode information about cosmic parameters. When analyzed using our best theoretical models, these measurements suggest the Hubble constant should be approximately 67 kilometers per second per megaparsec. However, direct measurements of nearby cosmic distances tell a different story. Astronomers use Cepheid variable stars as cosmic candles, stars whose brightness pulsates in predictable patterns that reveal their true luminosity. By comparing this intrinsic brightness to their observed brightness, astronomers can determine precise distances to nearby galaxies. These local measurements, when combined with observations of distant supernovae and other cosmic distance indicators, yield a Hubble constant of approximately 73 kilometers per second per megaparsec. While this difference might seem small, it represents a discrepancy of nearly 10%, far larger than the measurement uncertainties involved. The tension has persisted despite increasingly sophisticated observations and analysis techniques. Multiple independent teams using different methods have confirmed both measurements, suggesting that systematic errors are unlikely to explain the discrepancy. The disagreement appears to be genuine, pointing toward new physics or fundamental gaps in our cosmic model. Several explanations have been proposed to resolve this tension. Some involve modifications to the standard model of cosmology, perhaps requiring additional forms of dark energy or dark matter that behave differently in the early and late universe. These modifications could alter the expansion history in ways that reconcile the conflicting measurements. Other solutions propose new physics in the universe's earliest moments. Perhaps additional particles or forces influence cosmic evolution during epochs we cannot directly observe. These exotic components might have decayed or become inactive long ago, leaving subtle signatures in the cosmic expansion rate. The possibility of systematic errors in one or both measurement methods continues to be investigated. Cepheid distances might be affected by previously unknown astrophysical processes, or our theoretical understanding of the cosmic microwave background might require refinement. However, extensive cross-checks have failed to identify the convincing sources of systematic bias. More revolutionary solutions suggest that our fundamental understanding of space, time, or gravity might need revision. Perhaps general relativity requires modification on cosmic scales, or the universe's geometry differs from our current assumptions in subtle but important ways. The Hubble tension paradox represents more than just a measurement problem. It may herald the discovery of new physics that will reshape our understanding of cosmic evolution, like historical tensions that led to quantum mechanics and relativity. This discrepancy might point toward revolutionary advances in our comprehension of the universe's fundamental nature. Structure formation paradox. In the earliest epochs of cosmic history, the universe was remarkably smooth and uniform, filled with an almost perfectly homogeneous sea of hot gas and radiation. Yet, within just a few 100 million years after the Big Bang, this pristine uniformity had given way to a rich tapestry of cosmic structure. The first stars ignited, galaxies assembled, and vast networks of dark matter began organizing into the cosmic web we observe today. This rapid transformation presents the structure formation paradox, a puzzle about how complexity emerged so quickly from cosmic simplicity. The cosmic microwave background radiation provides a snapshot of the universe when it was only 380,000 years old, the moment when space cooled enough for atoms to form and light to travel freely for the first time. This ancient light reveals temperature variations of only 1 part in 100,000 across the entire sky, indicating that matter was distributed with extraordinary uniformity throughout the early cosmos. Yet, observations from powerful telescopes reveal fully formed galaxies existing when the universe was less than 1 billion years old, representing only 7% of its current age. These ancient galaxies contain billions of stars organized into rotating disks and elliptical structures, suggesting complex gravitational processes had already sculpted matter into sophisticated arrangements. The paradox deepens when we consider the physics of structure formation. Gravity, while relentless in its attractive pull, operates relatively slowly on cosmic scales. For small density fluctuations in the early universe to grow into galaxy-sized structures should require billions of years of gradual accumulation, not the rapid assembly we observe. Computer simulations of cosmic evolution help illuminate this mystery. These models begin with the tiny density variations observed in the cosmic microwave background and follow their evolution through billions of years of cosmic time. The simulations reveal that dark matter plays a crucial role in accelerating structure formation. Dark matter, which interacts gravitationally but not electromagnetically, began clustering immediately after the Big Bang without being slowed by radiation pressure. While ordinary matter remained coupled to photons and could not collapse efficiently, dark matter formed the gravitational scaffolding upon which normal matter would later accumulate. This head start allowed dark matter halos to form relatively quickly, creating deep gravitational wells that could capture and concentrate ordinary matter once it decoupled from radiation. The first stars formed within these dark matter structures, igniting when gas clouds reached sufficient density and temperature to begin nuclear fusion. Feedback processes from early star formation also played important roles in shaping cosmic structure. The first generation of massive stars lived brief, violent lives before exploding as supernovae, dispersing heavy elements throughout their surroundings and triggering additional waves of star formation in nearby regions. Supermassive black holes, somehow forming in the universe's earliest epochs, provided additional mechanisms for rapid structure assembly. These cosmic giants could merge with other black holes and accrete matter at prodigious rates, powering brilliant quasars that influence galaxy formation across vast distances. Recent observations have revealed that galaxy formation proceeded even more rapidly than previously thought. Some galaxies appear to have assembled most of their stellar mass within the first few 100 million years after the Big Bang, suggesting that the processes driving structure formation were remarkably efficient. The structure formation paradox highlights the dynamic nature of cosmic evolution and the intricate interplay between dark matter, ordinary matter, and energetic astrophysical processes. Understanding how the universe transitions so quickly from smooth uniformity to rich complexity remains one of astronomy's most active research frontiers, revealing new insights about the forces that shaped our cosmic home. Vanishing Star Paradox. Throughout human history, the stars have represented permanence and constancy, reliable beacons that guide navigation and mark the passage of seasons. Ancient astronomers mapped their positions with meticulous care, creating catalogs that documented the night sky's seemingly eternal patterns. Yet modern astronomical surveys have revealed a disturbing mystery. Some stars that once blazed brightly in historical records have completely vanished from the sky, disappearing without any obvious explanation. The Vanishing Star Paradox emerged from systematic comparisons between historical star catalogs and contemporary observations. When astronomers began digitizing old photographic plates and comparing them with modern sky surveys, they discovered that certain stars documented in earlier observations were simply no longer there. These weren't cases of stars becoming too faint to detect. They had vanished entirely, leaving no trace of their former existence. One of the most famous cases involves a star cataloged in the constellation Centaurus in the 1950s, which appeared as a normal, moderately bright star in multiple photographic surveys. When astronomers returned to observe this region decades later with more powerful telescopes, they found nothing at the star's recorded position. The star had not dimmed or moved, it had simply ceased to exist. Several explanations have been proposed for these stellar disappearances. The most conventional involves misidentification in historical records. Perhaps what appeared to be a single star was actually a binary system where one component underwent a catastrophic explosion, leaving behind a faint remnant that modern surveys cannot detect. Variable stars might also explain some cases, with stars that were bright during historical observations now residing in dim phases of their natural cycles. More dramatic possibilities involve direct stellar collapse into black holes without the typical supernova explosion. While most massive stars end their lives in brilliant supernovae that can outshine entire galaxies, certain theoretical models predict that some stars might collapse directly into black holes, effectively disappearing from the visible universe without fanfare. Failed supernovae represent another intriguing possibility. In these scenarios, a massive star begins the collapse process that should trigger a supernova explosion, but something goes wrong with the mechanism. Instead of exploding outward, the stellar material continues falling inward, creating a black hole while producing little or no visible light. Some researchers have proposed more exotic explanations involving hypothetical particles or processes beyond our current understanding of physics. These might include interactions with dark matter that could cause stars to collapse or transform in unexpected ways, or encounters with primordial black holes left over from the universe's earliest moments. The search for vanishing stars has been systematized through projects like the Vanishing and Appearing Sources During a Century of Observations program, which compares historical and modern astronomical data to identify objects that have appeared or disappeared over the past century. These surveys have cataloged dozens of candidate vanishing stars, though many cases remain ambiguous. Advanced monitoring systems now track millions of stars continuously, watching for any signs of unusual behavior or sudden disappearance. Time domain astronomy, which studies how cosmic objects change over time, has become increasingly sophisticated at detecting transient events and unusual stellar evolution. The implications of confirmed stellar vanishing extend beyond astrophysics into fundamental physics itself. If stars can indeed disappear through unknown mechanisms, it might indicate new physics operating on stellar scales, perhaps involving exotic matter or previously unknown forces. The Vanishing Star Paradox reminds us that even the most seemingly permanent features of our universe may be subject to processes we do not yet understand, challenging our assumptions about stellar evolution and the stability of cosmic structures. Superluminal expansion and paradox. One of the most counterintuitive aspects of our expanding universe appears to violate Einstein's fundamental principle that nothing can travel faster than light. Observations reveal that the most distant galaxies are receding from us at velocities that exceed the speed of light, creating what seems like an impossible contradiction with special relativity. This superluminal expansion paradox challenges our understanding of space, time, and the nature of cosmic motion itself. The paradox emerges from Hubble's discovery that distant galaxies are moving away from us, with more distant objects receding at higher velocities. This relationship, known as Hubble's law, indicates that the universe itself is expanding, carrying galaxies along with the stretching of space. When we extend this relationship to truly cosmic distances, we find galaxies so far away that their recession velocities exceed the speed of light. At first glance, this appears to violate special relativity, which states that no material object or information can travel faster than light through space. This speed limit represents a fundamental constraint on how quickly cause and effect can propagate through the universe, ensuring that the sequence of events remains consistent for all observers. The resolution lies in understanding the difference between motion through space and the expansion of space itself. Special relativity constrains how fast objects can move through the fabric of space-time, but it places no limits on how quickly space itself can expand. The galaxies that appear to recede faster than light are not actually moving through space at superluminal velocities. Instead, the space between us and these galaxies is expanding at a rate that creates the appearance of faster-than-light recession. This distinction becomes clearer when we consider the cosmic expansion in terms of scale factor, a quantity that describes how the size of the universe changes over time. As this scale factor increases, it stretches all distances proportionally, carrying distant objects away from each other without requiring them to move through space at high velocities. The expansion affects light itself in profound ways. Photons traveling from distant galaxies must traverse an ever-increasing amount of space as the universe expands during their journey. This stretches the wavelengths of the light, shifting it toward the red end of the spectrum, and providing the observational evidence for cosmic expansion through redshift measurements. The concept of the observable universe boundary illustrates this paradox clearly. Light from the most distant objects we can see has been traveling toward us for nearly the entire age of the universe. Yet these objects are now much farther away than when they emitted the light we observe. The current distance to these objects exceeds the distance light could have traveled in the age of the universe, placing them beyond what might naively be considered our cosmic horizon. Cosmic inflation, the period of exponential expansion in the universe's earliest moments, represents an even more dramatic example of superluminal expansion. During inflation, space expanded so rapidly that regions now separated by billions of light years were once in causal contact, explaining the observed uniformity of the cosmic microwave background radiation. This understanding has profound implications for our cosmic perspective. There exist regions of the universe that are receding from us so rapidly that light emitted from them today will never reach us, creating a fundamental limit to the information we can ever receive about the cosmos. The superluminal expansion also affects our definition of distance in cosmology. The distance to a remote galaxy can be defined in several ways. The distance light traveled to reach us, the current distance to the galaxy accounting for expansion, or the distance the galaxy was from us when it emitted the light we observe. The superluminal expansion paradox reveals how cosmic expansion operates beyond our everyday experience of motion, demonstrating that space itself can stretch faster than light while respecting the fundamental principles of relativity. Anthropic Paradox. The fundamental constants of nature appear to be precisely calibrated for the existence of complexity, structure, and ultimately life itself. This remarkable fine-tuning presents the Anthropic Paradox, one of the most profound puzzles in modern physics and cosmology. The strengths of the four fundamental forces, the masses of elementary particles, and the rate of cosmic expansion all seem to fall within incredibly narrow ranges that permit the formation of atoms, stars, planets, and the intricate chemistry necessary for biological processes. Consider the delicate balance required for stellar nucleosynthesis, the process by which stars forge heavy elements in their cores. If the strong nuclear force were slightly weaker, protons and neutrons could not bind together to form atomic nuclei, leaving the universe filled only with hydrogen. If this force were marginally stronger, hydrogen would fuse so readily that none would remain to fuel long-lived stars or form water molecules. The electromagnetic force displays similar precision in its calibration. A small increase in its strength would prevent electrons from binding to atomic nuclei, making atoms impossible. A decrease would cause electrons to spiral into nuclei, eliminating the electron shells that enable chemical bonding and molecular complexity. The masses of fundamental particles also appear remarkably well-tuned. If quarks were slightly heavier, neutrons would decay before they could form atomic nuclei. If electrons were more massive, atoms would be too small for complex chemistry. These mass relationships seem to exist within narrow windows that allow for the rich atomic and molecular diversity we observe. Cosmological parameters show equally striking fine-tuning. The initial density of the universe required extraordinary precision to permit structure formation. If density had been slightly higher, the universe would have collapsed before stars could form. If lower, matter would have dispersed too quickly for gravitational clustering to create galaxies and stellar systems. The cosmological constant, which drives the universe's accelerating expansion, presents perhaps the most extreme example of fine-tuning. Its observed value appears to be precisely calibrated to allow structure formation while avoiding cosmic collapse or runaway expansion. Several approaches attempt to address this apparent fine-tuning. The multiverse hypothesis proposes that our universe is one of countless others, each with different values for the fundamental constants. In this vast ensemble, some universes would naturally possess the precise conditions necessary for complexity and life. String theory provides a potential mechanism for generating such a multiverse. The theory suggests that additional spatial dimensions could be curled up in numerous different ways, each configuration producing different values for the constants we observe in our three-dimensional space. This landscape of possibilities might contain an enormous number of distinct universes. Alternatively, some physicists argue that the apparent fine-tuning reflects limitations in our understanding, rather than genuine cosmic coincidences. Perhaps future theories will reveal deeper principles that necessarily produce the observed values, making them seem less arbitrary and more inevitable. The anthropic principle itself offers another perspective, suggesting that we should not be surprised to find ourselves in a universe compatible with our existence. This reasoning argues that any observers will necessarily find themselves in a universe capable of producing observers, making the apparent fine-tuning a selection effect rather than a fundamental mystery. Critics point out that the anthropic approach may discourage the search for deeper physical understanding by accepting fine-tuning as an observational necessity rather than seeking explanations through more fundamental theories. The Anthropic Paradox touches on profound questions about the nature of existence, the role of consciousness in physics, and whether our universe represents a unique, precisely calibrated cosmos or one instance in an infinite sea of possibilities. Dark Matter Paradox. Across the vast reaches of space, an invisible presence makes itself known through gravity alone. This mysterious substance, called dark matter, comprises approximately 85% of all matter in the universe. Yet, it interacts with ordinary matter and energy only through gravitational forces. The dark matter paradox represents one of modern astronomy's greatest mysteries. How can something so abundant and influential remain completely hidden from direct detection? The evidence for dark matter's existence comes from numerous independent observations of cosmic structure and dynamics. When astronomers measure how fast stars orbit within galaxies, they find orbital velocities far too high for the visible matter alone to provide sufficient gravitational binding. Without additional invisible mass, these stars should fly away into intergalactic space, yet the galaxies remain intact and stable. Galaxy clusters, the largest gravitationally bound structures in the universe, provide even more compelling evidence. The hot gas within these clusters moves at speeds that require 10 times more gravitational mass than we observe in stars and visible matter. This invisible component reveals itself through gravitational lensing, where the cluster's total mass bends and distorts light from background galaxies in precisely the way Einstein's theory predicts. The cosmic microwave background radiation carries imprints of dark matter's influence from the universe's earliest epochs. The pattern of temperature fluctuations in this ancient light reflects the gravitational effects of dark matter clumping during the universe's first few 100,000 years. long before stars and galaxies formed. Computer simulations of cosmic structure formation require dark matter to reproduce the observed distribution of galaxies and galaxy clusters. Without this invisible component, the simulations produce a universe that looks nothing like what telescopes reveal, while including dark matter creates cosmic structures that match observations with remarkable precision. Despite this overwhelming gravitational evidence, decades of sophisticated experiments have failed to detect dark matter particles directly. Deep underground laboratories shield sensitive detectors from cosmic rays and background radiation, waiting for the subtle signature of a dark matter particle colliding with ordinary matter. These experiments have achieved extraordinary sensitivity, yet dark matter remains stubbornly elusive. Particle accelerators like the Large Hadron Collider attempt to create dark matter particles by smashing protons together at enormous energies. If dark matter consists of particles that can be produced in high-energy collisions, these experiments should detect the characteristic signatures of dark matter creation and decay. So far, no convincing signals have emerged. Theoretical physicists have proposed numerous candidates for dark matter particles. Weakly interacting massive particles, or WIMPs, represent the most studied possibility. Hypothetical particles that interact through gravity, and the weak nuclear force but not through electromagnetism. Axions, extremely light particles originally proposed to solve other problems in particle physics, offer another compelling candidate. Alternative theories suggest that dark matter might not consist of particles at all, but rather represents a modification to our understanding of gravity itself. These approaches propose that gravitational forces behave differently on cosmic scales than Einstein's theory predicts, potentially eliminating the need for invisible matter entirely. Sterile neutrinos, hypothetical particles that interact even more weakly than ordinary neutrinos, could comprise dark matter while remaining virtually undetectable by current methods. These particles would influence cosmic structure through gravity while remaining invisible to electromagnetic and nuclear forces. The dark matter paradox highlights the profound limitations in our understanding of the universe's fundamental composition. Something that dominates cosmic structure and influences the formation of every galaxy remains completely mysterious, challenging our theories and experimental capabilities while shaping the very architecture of existence itself. Dark energy paradox. In the depths of empty space lies a force so mysterious and pervasive that it shapes the fate of the entire universe. Yet we understand almost nothing about its true nature. This enigmatic influence, called dark energy, drives the accelerating expansion of space itself, pushing galaxies apart at an ever-increasing rate. The dark energy paradox represents one of the most profound mysteries in modern cosmology. What is this invisible force that comprises nearly 70% of everything that exists? The discovery of dark energy came as a complete surprise to astronomers in the late 20th century. By studying distant supernovae, stellar explosions that serve as cosmic lighthouses with known brightness, researchers expected to measure how gravity was slowing the universe's expansion over time. Instead, they found something extraordinary. The expansion was actually speeding up, as if some unseen energy was pushing space apart with ever greater force. This acceleration contradicts our intuitive understanding of gravity as an attractive force. In a universe filled only with matter and radiation, gravity should gradually slow the expansion that began with the Big Bang, eventually bringing it to a halt, or even reversing it into a cosmic collapse. The observation that expansion is accelerating suggests that a repulsive force dominates the universe's energy budget. The nature of dark energy remains deeply mysterious. Unlike matter, which becomes less dense as the universe expands, dark energy appears to maintain constant density even as space stretches. This means that as the universe grows larger, the total amount of dark energy increases, providing an ever stronger push that accelerates cosmic expansion. Einstein's equations of general relativity can accommodate this accelerating expansion through the cosmological constant, a term he originally introduced to allow for a static universe. This constant represents the energy density of empty space itself, suggesting that the vacuum contains a uniform field that exerts negative pressure, pushing space apart rather than pulling it together. However, when physicists attempt to calculate the vacuum energy density from quantum field theory, they encounter a staggering discrepancy. The theoretical prediction exceeds the observed value by more than 100 orders of magnitude, representing the largest mismatch between theory and observation in all of science. This enormous disagreement suggests that our understanding of either quantum mechanics or gravity is fundamentally incomplete. Alternative explanations for dark energy include dynamic fields that change over time, similar to the field thought to have driven cosmic inflation in the universe's earliest moments. These quintessence models propose that dark energy might strengthen or weaken as the universe evolves, potentially leading to different cosmic futures than a constant dark energy would predict. Some theories suggest that dark energy might not be a fundamental force at all, but rather an illusion created by our particular location in an inhomogeneous universe. If we happen to live in a region of lower density surrounded by denser areas, the resulting gravitational effects might mimic the appearance of accelerating expansion. More radical proposals involve modifications to general relativity itself on cosmic scales. These theories suggest that gravity might behave differently over vast distances than Einstein's equations predict, creating the appearance of dark energy while actually representing a breakdown in our understanding of gravitational physics. The future evolution of dark energy holds profound implications for the ultimate fate of the universe. If dark energy continues to accelerate expansion at its current rate, galaxies will eventually become isolated islands in an increasingly cold and empty cosmos. Stars will exhaust their fuel, black holes will evaporate, and the universe will fade into a state of maximum entropy. The dark energy paradox challenges our most basic assumptions about the nature of space, time, and energy, reminding us that the vast majority of our universe remains completely mysterious, operating according to principles we have yet to discover or understand. Inflation Paradox. In the first infinitesimal fraction of a second after the Big Bang, the universe underwent a period of expansion so rapid and dramatic that it defies comprehension. During this epoch, called cosmic inflation, space stretched exponentially, growing from a region smaller than a subatomic particle to a size larger than a grapefruit in less than a trillionth of a trillionth of a trillionth of a second. The inflation paradox asks a fundamental question. What could possibly cause such extraordinary expansion in the universe's earliest moments? The paradox emerges from several puzzling observations about our universe that standard Big Bang theory cannot explain. The cosmic microwave background radiation shows that regions of space separated by vast distances have nearly identical temperatures. Yet, according to conventional physics, these regions should never have been close enough to exchange energy and reach thermal equilibrium. Additionally, the universe appears to be remarkably flat in its overall geometry, requiring initial conditions so precisely tuned that the probability of achieving them by chance approaches zero. The absence of exotic relics like magnetic monopoles, which many theories predict should have formed in the early universe, presents another puzzle that standard cosmology struggles to address. Cosmic inflation provides an elegant solution to these problems by proposing that the universe underwent a brief but violent period of exponential expansion. During this phase, a tiny, causally connected region of space-time was stretched to enormous proportions, carrying the seeds of our entire observable universe within its expanding boundaries. The driving force behind inflation is thought to be a scalar field called the inflaton, which filled space with a special type of energy that created gravitational repulsion rather than attraction. Unlike ordinary matter and energy, which become less dense as space expands, the inflaton field maintained constant energy density throughout the inflationary epoch, providing a sustained push that drove exponential expansion. This process explains the universe's observed uniformity by suggesting that all regions we can observe today were once close enough to interact and reach the same temperature before inflation stretched them to cosmic proportions. The apparent fine-tuning of the universe's flatness becomes natural, as any initial curvature would have been stretched to imperceptible levels by the rapid expansion. The paradox deepens when we consider what could trigger such a process and, perhaps more mysteriously, what could bring it to an end. The inflaton field must have possessed very specific properties to drive inflation for just the right amount of time, Too little, and the universe's problems remain unsolved. Too much, and space would expand so rapidly that no structures could ever form. Quantum fluctuations in the inflaton field during inflation provide a remarkable connection between the quantum world and cosmic structure. These microscopic variations were stretched to astronomical scales, becoming the density fluctuations that eventually grew into the galaxies and galaxy clusters we observe today. The cosmic microwave background radiation preserves an imprint of these quantum fluctuations, offering direct observational evidence for inflation's quantum origins. Various models attempt to describe the specific mechanism that ended inflation, typically involving the inflaton field rolling down a potential energy landscape until it reached a state where normal expansion could resume. This transition, called reheating, converted the inflaton's energy into the hot, dense state of ordinary matter and radiation that characterizes the conventional Big Bang scenario. The inflation paradox extends beyond physics into questions about the nature of space and time themselves. If inflation can occur once, why not multiple times? Some theories suggest that inflation might be an eternal process, creating a multiverse where new regions of space-time constantly undergo inflationary expansion. Modern observations continue to test inflation's predictions with increasing precision, examining the cosmic microwave background and searching for gravitational waves that inflation should have produced. These studies probe the universe's first moments, seeking to understand the mysterious process that shaped everything we observe. Planck scale paradox. At the smallest conceivable scales of existence lies a realm where our most fundamental theories of physics break down completely. The Planck scale, named after physicist Max Planck, represents the boundary beyond which our current understanding of space, time, and matter loses all meaning. This paradox challenges us to comprehend what might exist at distances of 10 to the power of minus 35 meters and time intervals of 10 to the power of minus 44 seconds, scales so tiny that they make atoms appear as vast as galaxies. The Planck scale emerges naturally from the fundamental constants of nature, the speed of light, Planck's constant from quantum mechanics, and Newton's gravitational constant. When these universal parameters are combined, they define natural units of length, time, and energy that appear to represent the ultimate limits of physical reality. Below these scales, the very concepts of distance and duration may cease to have any meaningful interpretation. At Planck scale dimensions, quantum mechanics and general relativity collide in ways that our current theories cannot describe. Quantum mechanics reveals that space and time themselves become subject to uncertainty principles, fluctuating wildly at the smallest scales. Meanwhile, general relativity suggests that such tiny regions would contain so much gravitational curvature that they would form microscopic black holes, creating paradoxes that neither theory can resolve independently. The paradox becomes even more perplexing when we consider that according to quantum field theory, empty space at the Planck scale should be a seething foam of virtual particles and antiparticles, constantly appearing and annihilating in time frames shorter than any possible measurement. This quantum foam might represent the fundamental structure of space-time itself, suggesting that smooth, continuous space is merely an approximation that emerges at larger scales. String theory attempts to address the Planck scale paradox by proposing that the most fundamental constituents of reality are not point particles, but tiny vibrating strings existing at precisely these scales. In this framework, different vibrational modes of these strings correspond to different particles and forces, potentially unifying all of physics within a single theoretical structure that operates naturally at Planck dimensions. Loop quantum gravity offers an alternative approach, suggesting that space-time itself is quantized into discrete units at the Planck scale. Rather than being infinitely divisible, space and time might consist of indivisible atoms of geometry, creating a granular structure to reality that becomes apparent only at the smallest possible scales. The implications of the Planck scale paradox extend far beyond theoretical physics. If space and time are indeed quantized at these scales, it might place fundamental limits on computation and information processing. The universe itself might operate like a vast quantum computer, with the Planck scale representing the smallest possible bits of information that can be processed or stored. Black holes provide a unique window into Planck scale physics. Near the center of a black hole, gravitational forces become so intense that quantum effects at the Planck scale might dominate the physics, potentially preventing the formation of true singularities. Instead, quantum gravity effects might halt gravitational collapse at Planck dimensions, creating exotic objects whose internal structure remains completely mysterious. The cosmic microwave background radiation might preserve subtle imprints of Planck-scale physics from the universe's earliest moments. During cosmic inflation, quantum fluctuations at the Planck scale were stretched to astronomical proportions, potentially embedding signatures of quantum gravity in the patterns of temperature variation we observe across the sky. Experimental investigation of the Planck scale presents seemingly insurmountable challenges. The energies required to probe these dimensions would exceed those achievable by any conceivable particle accelerator by many orders of magnitude. Even theoretical investigation pushes mathematics to its limits, requiring new mathematical frameworks that can describe physics in regimes where space and time themselves become uncertain. The Planck scale paradox represents the ultimate frontier of human knowledge, challenging us to imagine what lies beyond the smallest meaningful scales of existence and questioning whether reality itself has a fundamental granular structure. Galaxy rotation curve paradox. When astronomers first began measuring how fast stars orbit within spiral galaxies, they expected to find a simple pattern reflecting the distribution of visible matter. Just as planets in our solar system orbit more slowly at greater distances from the Sun, stars in the outer regions of galaxies should move more slowly than those near the galactic center, where most of the visible mass is concentrated. Instead, observations revealed something completely unexpected. Stars throughout the galaxy's disk orbit at roughly the same speed, creating flat rotation curves that seem to defy the laws of gravity. This galaxy rotation curve paradox emerged in the 1970s when astronomer Vera Rubin and her colleagues used sophisticated spectrographs to measure the velocities of stars in the Andromeda Galaxy and other nearby spirals. The results were shocking. Instead of the declining velocities predicted by Newton's laws, the rotation curves remained flat, far beyond the visible edge of the galactic disk. The implications are profound. If only the visible matter in a galaxy contributed to its gravitational field, stars in the outer regions should be moving so slowly that many would escape the galaxy's gravitational grip entirely. The observed flat rotation curves indicate that these distant stars are orbiting much faster than the visible matter alone could support, suggesting the presence of additional unseen mass throughout the galactic disk. The discrepancy becomes more dramatic at larger distances from the galactic center. While the visible matter in a typical spiral galaxy is concentrated primarily in the central bulge and disk, the rotation curves indicate that the gravitational mass continues to increase linearly with distance, even in regions where few or no stars are visible. This observation provided some of the first compelling evidence for dark matter, an invisible form of matter that interacts gravitationally but not electromagnetically. To explain the flat rotation curves, dark matter must be distributed in an extended halo surrounding each galaxy, with far more dark matter than visible matter in the outer regions. Computer models of galaxy formation require dark matter halos to reproduce the observed rotation curves. These simulations suggest that dark matter forms the gravitational scaffolding upon which normal matter accumulates to form stars and gas clouds. Without this invisible component, the models cannot create galaxies that match what telescopes observe. The rotation curve paradox extends beyond individual galaxies to galaxy clusters and larger cosmic structures. The velocities of galaxies within clusters also exceed what the visible matter alone could gravitationally bind, requiring additional dark matter to explain why these vast collections of galaxies hold together instead of dispersing into space. Alternative explanations have been proposed that modify our understanding of gravity itself, rather than invoking invisible matter. Modified Newtonian dynamics, or MOND, suggests that gravitational forces might behave differently at the extremely weak accelerations characteristic of galactic outskirts. These theories attempt to explain flat rotation curves, by proposing that gravity becomes stronger than Newton's laws predict when accelerations fall below a certain threshold. Recent observations using advanced radio telescopes have extended rotation curve measurements to even greater distances from galactic centers, revealing that the flat rotation pattern continues far beyond the visible disk in many galaxies. These observations provide increasingly precise tests of both dark matter models and alternative gravity theories. The discovery of ultra-diffuse galaxies, which appear to contain very little dark matter despite their large size, has added new complexity to the rotation curve paradox. These unusual objects seem to violate the expected relationship between visible and dark matter, challenging our understanding of how galaxies form and evolve. The galaxy rotation curve paradox remains one of the most important unsolved problems in astrophysics, touching on fundamental questions about the nature of matter, gravity, and cosmic structure formation. Emerging galaxies, paradox. The universe expands relentlessly, carrying distant galaxies away from each other at velocities that increase with distance. Yet, throughout cosmic history, galaxies have been colliding and merging with remarkable frequency. This apparent contradiction presents the merging galaxies paradox. How can galaxies crash into each other if the expansion of space is pushing them apart? The resolution reveals the subtle interplay between cosmic expansion and local gravitational attraction that shapes the evolution of cosmic structure. The key to understanding this paradox lies in recognizing that cosmic expansion affects different scales in dramatically different ways. While space itself stretches uniformly throughout the universe, this expansion only dominates the motion of objects separated by truly vast distances. On smaller scales, gravity can overcome the expansion and pull objects together, creating bound systems that resist the universal stretching of space. Our own Milky Way galaxy exists within the local group, a collection of several dozen galaxies bound together by their mutual gravitational attraction. Despite the overall expansion of the universe, the galaxies within this group orbit around their common center of mass, occasionally approaching close enough to interact gravitationally, or even merge completely. The most dramatic example visible from Earth is the approaching collision between the Milky Way and the Andromeda Galaxy. Despite being separated by over 2 million light-years, these two massive spirals are moving toward each other at approximately 250,000 miles per hour. In about 4.5 billion years, they will collide and merge, creating a single giant elliptical galaxy that astronomers have nicknamed Milkomeda. This collision occurs because the local group represents a gravitationally bound system, where the attractive forces between galaxies overcome the expansion of space. Within such bound regions, the usual rules of cosmic expansion do not apply. Instead, the galaxies follow complex orbital paths determined by their gravitational interactions, sometimes leading to spectacular collisions. The paradox extends to understanding why galaxy mergers were even more common in the early universe, when cosmic expansion was presumably stronger. Observations of distant galaxies reveal numerous examples of galactic collisions and mergers occurring when the universe was younger and smaller. During these earlier epochs, galaxies were closer together on average, making gravitational interactions more likely despite the rapid expansion. Computer simulations of cosmic structure formation show that galaxy mergers play a crucial role in shaping the universe we observe today. Large elliptical galaxies, which dominate the centers of galaxy clusters, are thought to have formed primarily through the merger of smaller spiral galaxies over billions of years. These violent collisions can trigger bursts of star formation, feed supermassive black holes, and completely reshape galactic structure. The Hubble Space Telescope has captured stunning images of galaxies in various stages of merger, from early gravitational encounters that create tidal streams of stars to final coalescence phases where two galactic nuclei spiral toward each other. These observations provide snapshots of the merger process that plays out over hundreds of millions of years. Dark matter plays a significant role in galaxy mergers, as the invisible halos surrounding each galaxy interact gravitationally long before the visible components begin to merge. Computer simulations show that dark matter halos can merge and blend, while the stellar components remain relatively intact. creating complex dynamics that influence the final outcome of galactic collisions. The rate of galaxy mergers has decreased significantly since the early universe, as cosmic expansion has carried most galaxies beyond the reach of gravitational interaction. Today, major mergers are relatively rare events, though minor mergers involving small satellite galaxies continue to occur regularly around massive systems like our own Milky Way. Understanding the merging galaxies paradox illuminates the ongoing tension between cosmic expansion and gravitational collapse that shapes structure formation throughout the universe, revealing how local physics can overcome global cosmological trends. Schrödinger's cat. In the realm of quantum mechanics lies one of the most famous thought experiments in all of science, a paradox that challenges our fundamental understanding of reality itself. Schrödinger's cat, proposed by physicist Erwin Schrödinger in 1935, presents a scenario so bizarre that it seems to violate common sense. A cat that exists in a state of being simultaneously alive and dead until someone opens a box to observe it. The paradox begins with a sealed box containing a cat alongside a diabolical device. Inside the box sits a Geiger counter monitoring a single radioactive atom that has a 50% chance of decaying within 1 hour. If the atom decays, the Geiger counter triggers a mechanism that breaks a flask of poison, killing the cat. If the atom does not decay, the cat remains alive and well. According to quantum mechanics, the radioactive atom exists in a superposition of states before measurement. It is both decayed and not decayed simultaneously. This quantum superposition represents one of the most fundamental aspects of the microscopic world, where particles can exist in multiple states until the act of observation forces them to choose a definite outcome. Schrödinger designed this thought experiment to illustrate what he saw as an absurd consequence of applying quantum mechanics to macroscopic objects. If the atom's quantum superposition determines the cat's fate, then the cat itself should exist in a superposition of being both alive and dead until someone opens the box to observe it. This scenario highlights the measurement problem in quantum mechanics, the mysterious process by which quantum systems transition from existing in multiple states simultaneously to having definite properties when observed. The paradox forces us to confront uncomfortable questions about the nature of reality and the role of observation in determining physical outcomes. Several interpretations attempt to resolve this paradox. The Copenhagen interpretation suggests that quantum superposition applies only to microscopic systems, and that the act of measurement by a macroscopic detector causes the quantum state to collapse into a definite outcome. In this view, the cat is never actually in superposition. The quantum uncertainty resolves as soon as the atom interacts with the detection apparatus. The many worlds interpretation offers a radically different solution, proposing that both outcomes occur simultaneously in parallel universes. When the atom decays or fails to decay, reality branches into separate worlds, one containing a live cat and another containing a dead cat. Each version of reality continues to exist, but observers can only experience one branch at a time. Decoherence theory provides another perspective, suggesting that interaction with the environment rapidly destroys quantum superposition in macroscopic systems. The cat, the box, and surrounding air molecules create a complex web of interactions that makes superposition practically impossible to maintain for objects larger than individual atoms or molecules. Modern experiments have created quantum superposition in increasingly large systems, from individual photons and electrons to molecules containing thousands of atoms. These studies probe the boundary between the quantum and classical worlds, investigating how and why the strange rules of quantum mechanics give way to the definite reality we experience in everyday life. The paradox extends beyond physics into philosophy, raising fundamental questions about consciousness and observation. Does the cat's fate depend on human observation? Or would any interaction with the environment suffice to determine the outcome? These questions touch on the deep relationship between mind and matter that quantum mechanics seems to suggest. Recent advances in quantum technology have made it possible to create and control quantum superposition in laboratory settings, leading to applications in quantum computing and quantum cryptography. These developments demonstrate that the strange world Schrödinger's cat inhabits represents genuine physical phenomena, Schrödinger's cat remains one of the most powerful illustrations of quantum mechanics' challenge to our intuitive understanding of reality, reminding us that the universe operates according to principles that often defy our everyday experience. EPR Paradox. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a thought experiment that would forever change our understanding of quantum mechanics and the nature of reality itself. The EPR paradox, named after its creators, challenges one of quantum theory's most unsettling predictions, that two particles can become entangled, sharing an instantaneous connection that persists regardless of the distance separating them, seemingly violating the fundamental principle that nothing can travel faster than light. The paradox begins with two particles that interact and become quantum entangled, creating a shared quantum state, where measuring one particle immediately determines the properties of its partner, no matter how far apart they have traveled. Einstein famously dismissed this phenomenon as spooky action at a distance, arguing that such instantaneous connections violated the principle of locality, the idea that objects can only be influenced by their immediate surroundings. Einstein, Podolsky, and Rosen proposed that quantum mechanics must be incomplete. They suggested that particles possess hidden variables, predetermined properties that determine measurement outcomes, without requiring mysterious instantaneous connections. In their view, entangled particles appeared correlated because they shared these hidden characteristics from the moment of their interaction, not because they maintained ongoing communication across space. The EPR thought experiment involves measuring complementary properties of entangled particles, such as their spin along different axes. Quantum mechanics predicts that these properties remain undefined until measurement, with the act of observation on one particle instantly determining the corresponding property of its distant partner. This seemed to require information to travel instantaneously between the particles, conflicting with special relativity's speed limit. For decades, the EPR paradox remained a philosophical debate rather than an experimental question. The situation changed dramatically in 1964, when physicist John Bell derived mathematical inequalities that could distinguish between quantum mechanics and hidden variable theories. Bell's theorem showed that local hidden variable theories must satisfy certain statistical relationships that quantum mechanics violates. Experimental tests of Bell's inequalities began in the 1970s and have consistently confirmed quantum mechanics predictions, while ruling out local hidden variable theories. These experiments create pairs of entangled photons and measure their properties along different directions, finding correlations that exceed what any local theory can explain. The resolution of the EPR paradox reveals that quantum entanglement does not actually transmit information faster than light. While measuring one entangled particle instantly affects its partner's quantum state, this influence cannot be used to send messages or signals. The correlations between entangled particles are genuine, but they become apparent only when observers compare their measurement results through conventional, slower-than-light communication. Modern understanding recognizes quantum entanglement as a fundamental feature of reality, rather than a flaw in quantum theory. Entanglement has become the foundation for emerging technologies including quantum computing, quantum cryptography, and quantum teleportation. These applications harness the strange correlations that Einstein found so troubling to perform tasks impossible with classical physics. Quantum entanglement experiments have been performed over increasingly large distances, from laboratory benches to satellite communications spanning thousands of kilometers. These studies confirm that entangled correlations persist regardless of separation, supporting quantum mechanics' most counterintuitive predictions about the interconnected nature of reality. The EPR paradox ultimately forced physicists to abandon classical intuitions about locality and separability. The universe appears to be fundamentally non-local, with quantum systems maintaining correlations that transcend the boundaries of space and time in ways that classical physics cannot explain. The EPR paradox demonstrates how quantum mechanics challenges our deepest assumptions about reality, revealing a universe where distant objects can share instantaneous correlations while respecting the speed limit that governs all physical interactions. Quantum Zeno Paradox. In the strange world of quantum mechanics, the very act of observation can fundamentally alter the behavior of physical systems in ways that defy classical intuition. The quantum Zeno paradox, named after the ancient Greek philosopher Zeno of Elea, presents one of the most counterintuitive aspects of quantum theory. Frequent observation of a quantum system can effectively freeze its evolution, preventing change through the mere act of measurement. The paradox draws its inspiration from Zeno's classical paradox of the arrow, which argued that a flying arrow must be motionless at each instant in time, leading to the conclusion that motion itself is impossible. The quantum version presents an equally puzzling scenario, where continuous observation can halt the natural evolution of quantum systems, creating a form of temporal paralysis through measurement. Consider a radioactive atom that has a certain probability of decaying over time. According to quantum mechanics, the atom exists in a superposition of decayed and undecayed states, with the probability of finding it decayed increasing gradually as time passes. However, if we frequently check whether the atom has decayed, each measurement resets the quantum state, reducing the likelihood that decay will occur. This effect arises from the fundamental nature of quantum measurement, which causes the collapse of quantum superposition into definite states. When we measure an undecayed atom, we project it back into the undecayed state, effectively resetting its quantum evolution. If measurements occur frequently enough, the atom never has sufficient time between observations to develop a significant probability of being found in the decayed state. The mathematics underlying this phenomenon reveals that the survival probability of a quantum system under frequent measurement approaches 100% as the measurement frequency increases toward infinity. This suggests that sufficiently rapid observation can make radioactive decay, chemical reactions, and other quantum processes essentially impossible to occur. Experimental demonstrations of the quantum Zeno effect have been performed using various quantum systems, from individual atoms trapped in electromagnetic fields to photons passing through optical devices. These experiments confirm that frequent measurement can indeed slow or halt quantum evolution, transforming theoretical predictions into observable phenomena. The effect has practical implications for quantum technology and quantum computing. Quantum information systems rely on maintaining delicate quantum superposition of states that are easily disrupted by environmental interference. The quantum Zeno effect suggests that carefully timed measurements might help preserve quantum states by preventing unwanted evolution and decoherence. Paradoxically, the opposite effect, called the anti-Zeno effect, can also occur under certain conditions. Instead of inhibiting quantum evolution, frequent measurements can sometimes accelerate it, causing systems to evolve more rapidly than they would without observation. The specific outcome depends on the precise timing of measurements and the nature of the quantum system being observed. The quantum Zeno paradox raises profound questions about the role of measurement in quantum mechanics and the relationship between observation and physical reality. It suggests that consciousness or measurement apparatus plays an active role in determining the course of physical events, challenging the classical notion of an objective reality that exists independently of observation. Recent research has explored applications of the quantum Zeno effect in quantum error correction, where strategic measurements might help protect quantum information from decay and corruption. These studies investigate how the paradoxical relationship between observation and evolution might be harnessed for practical quantum technologies. The quantum Zeno paradox exemplifies quantum mechanics' challenge to our classical understanding of causality and measurement, revealing a universe where observation itself becomes a powerful force capable of altering natural processes. Wigner's friend paradox. The role of consciousness in quantum mechanics reaches its most perplexing expression in Wigner's friend paradox, a thought experiment that pushes the measurement problem to its logical extreme. Proposed by Nobel laureate Eugene Wigner in 1961, this paradox explores what happens when one observer watches another observer make a quantum measurement, creating a scenario where two conscious beings can apparently hold contradictory views about the same physical reality. The setup begins with Wigner's friend isolated in a laboratory, preparing to measure the spin of a quantum particle that exists in superposition. simultaneously spinning up and down until observed. According to quantum mechanics, the particle remains in this superposition state until the friend performs a measurement, at which point the quantum wave function collapses and the particle assumes a definite spin direction. From the friend's perspective inside the laboratory, the measurement yields a clear result. The particle is found spinning either up or down with equal probability. The act of observation has collapsed the superposition, and the friend now knows the particle's definite state. Reality appears concrete and well-defined from this internal viewpoint. However, Wigner observes the entire laboratory from outside, treating both his friend and the quantum particle as parts of a larger quantum system. From Wigner's external perspective, if he has not yet communicated with his friend, the entire laboratory, including the friend, the measuring apparatus, and the particle, remains in quantum superposition. The friend exists in a superposition of having measured spin up and having measured spin down. This creates a disturbing contradiction. The friend believes the measurement has yielded a definite result and collapsed the wave function, while Wigner maintains that the system, including his friend, remains in superposition. Both observers are conscious and competent, yet they disagree about fundamental aspects of reality. The paradox becomes even more troubling when we consider what happens when Wigner finally communicates with his friend. According to standard quantum mechanics, this communication should collapse the larger superposition, forcing the system into one definite state. But this suggests that Wigner's consciousness plays a special role in determining physical reality, a conclusion that many physicists find deeply uncomfortable. Various interpretations of quantum mechanics handle this paradox differently. The Copenhagen interpretation might suggest that consciousness plays a fundamental role in wave function collapse, making Wigner's perspective privilege over his friends. However, this leads to uncomfortable questions about what constitutes consciousness and why some observers should be more fundamental than others. The many worlds interpretation avoids the contradiction by proposing that both outcomes occur simultaneously in parallel universes. When the friend measures the particle, reality branches into two worlds, one where the friend observes spin up and another where the friend observes spin down. Wigner's later observation simply determines which branch of reality he experiences. Recent extensions of Wigner's paradox involve multiple friends making measurements in different laboratories, creating even more complex scenarios where different observers can hold incompatible views about quantum measurements performed by others. These extended versions push the paradox to new extremes, suggesting that objective reality might not exist in any meaningful sense. Experimental tests inspired by Wigner's friend have been proposed and performed using quantum systems where photons play the role of friends making measurements. These experiments reveal genuine inconsistencies in how different observers describe the same quantum events, confirming that the paradox reflects real features of quantum mechanics rather than mere philosophical speculation. Wigner's friend paradox represents one of quantum mechanics' most challenging puzzles, forcing us to confront the possibility that reality itself might be observer-dependent and that consciousness plays a more fundamental role in physics than classical science ever imagined. Measurement problem. At the heart of quantum mechanics lies a profound mystery that has puzzled physicists for nearly a century: the measurement problem. This fundamental puzzle asks when and how a quantum system transitions from existing in multiple states simultaneously to having the single, definite properties we observe in measurements. The problem strikes at the core of our understanding of reality, questioning the very nature of physical existence and the role of observation in determining outcomes. Quantum mechanics describes microscopic systems using wave functions that evolve smoothly and deterministically according to the Schrödinger equation. These wave functions represent superposition states where particles can exist in multiple locations, have various energies, or spin in different directions simultaneously. This mathematical description has proven extraordinarily successful at predicting the statistical outcomes of quantum experiments. However, whenever we actually measure a quantum system, we never observe superposition directly. Instead, we always find the system in one definite state: a particle detected at a specific location, an electron with definite spin, or an atom in a particular energy level. The measurement process somehow forces the quantum system to choose one outcome from the many possibilities encoded in its wave function. This transition from quantum superposition to classical definiteness appears to involve a fundamental discontinuity in physical processes. The smooth, deterministic evolution described by quantum mechanics suddenly gives way to random, probabilistic outcomes that cannot be predicted with certainty. This apparent contradiction between the theory's mathematical formalism and experimental observations constitutes the measurement problem. The challenge becomes even more perplexing when we consider what constitutes a measurement. Does the quantum to classical transition require conscious observation by a human being? Or can any interaction with a macroscopic apparatus trigger wave function collapse? If consciousness is not required, then what physical process determines when and how the transition occurs? Various interpretations of quantum mechanics propose different solutions to the measurement problem. The Copenhagen interpretation suggests that wave function collapse is a fundamental aspect of nature that occurs whenever a quantum system interacts with a classical measuring device. However, this approach requires an arbitrary boundary between quantum and classical realms, without specifying where this boundary lies. Objective collapse theories propose that wave function collapse is a real physical process that occurs spontaneously in quantum systems, with the probability of collapse increasing with system size and complexity. These theories suggest that macroscopic objects cannot maintain superposition because they collapse too rapidly, naturally explaining why we never observe everyday objects in quantum superposition. The many worlds interpretation eliminates the measurement problem by denying that wave function collapse ever occurs. Instead, all possible measurement outcomes happen simultaneously in parallel universes, with observers experiencing only one branch of the infinite tree of possibilities. In this view, apparent randomness reflects our inability to perceive the other branches of reality. Decoherence theory offers another perspective, suggesting that interaction with the environment rapidly destroys quantum superposition in macroscopic systems. The complex web of interactions between a quantum system and its surroundings creates entanglement that effectively localizes quantum states, making superposition practically unobservable without requiring fundamental collapse. Recent experimental advances have made it possible to create and maintain quantum superposition in increasingly large systems, from individual molecules to collections of thousands of atoms. These studies probe the boundary between quantum and classical behavior, testing different theories about when and why quantum superposition gives way to classical definiteness. The measurement problem remains one of quantum mechanics' deepest unsolved mysteries, challenging our fundamental understanding of how the microscopic quantum world gives rise to the definite classical reality we experience. Quantum tunneling paradox. Imagine standing before a towering mountain, knowing that, according to all logic, you cannot walk through solid rock. Yet in the quantum world, particles accomplish exactly this seemingly impossible feat every single day. The quantum tunneling paradox challenges our fundamental understanding of barriers and boundaries. In our everyday experience, objects need sufficient energy to overcome obstacles. A ball thrown at a wall either bounces back or breaks through if thrown hard enough. But quantum particles operate under entirely different rules. They possess a strange ability to appear on the other side of energy barriers without actually having enough energy to climb over them. This phenomenon occurs because particles at the quantum scale exist as probability waves rather than solid objects. When a particle encounters a barrier, its wave function doesn't simply stop at the boundary. Instead, it extends slightly into and beyond the barrier, creating a small but real probability that the particle will be found on the other side. The mathematics reveals something extraordinary. Even when a particle has far less energy than required to surmount a barrier, there remains a chance it will tunnel through. This probability decreases exponentially with barrier thickness and height, but it never reaches absolute zero. For a barrier just a few atoms thick, particles tunnel through with surprising frequency. This paradox manifests everywhere in nature. Nuclear fusion in stars relies on protons tunneling through the electromagnetic barrier that should repel them. Without quantum tunneling, our sun would be a cold, dark sphere, and life on Earth would never have begun. The very atoms in your body were forged through processes that depend on this paradoxical behavior. Modern technology harnesses quantum tunneling in the countless ways. Scanning tunneling microscopes use the phenomenon to image individual atoms. Electronic devices rely on tunnel junctions, and quantum computers exploit tunneling effects for their revolutionary capabilities. The paradox deepens when we consider measurement. Before observation, we can only speak of probabilities. The particle exists in a superposition of states, simultaneously on both sides of the barrier. Only upon measurement does reality collapse into a definite outcome. What makes this truly puzzling is that the particle doesn't gradually seep through the barrier like water through a membrane. It instantaneously appears on the other side, as if teleporting across forbidden territory. The tunneling process itself takes no measurable time, adding another layer of mystery to an already bewildering phenomenon. The implications extend far beyond laboratory curiosities. Quantum tunneling affects the stability of matter itself. Without it, the protons in atomic nuclei would fly apart, unable to overcome their mutual electromagnetic repulsion. The delicate balance between tunneling and nuclear forces determines which elements can exist in our universe. Even the process of cellular respiration relies on quantum tunneling. Enzymes facilitate biochemical reactions by lowering energy barriers, but even these reduced barriers often require tunneling effects for reactions to proceed at biological temperatures. The very chemistry of life depends on particles defying classical physics. The paradox also influences our understanding of the early universe. During cosmic inflation, quantum fluctuations tunneled across energy barriers, creating the density variations that eventually became galaxies and stars. The large-scale structure of the cosmos bears the fingerprints of quantum tunneling events that occurred in the universe's first moments. Perhaps most remarkably, quantum tunneling suggests that nothing in the universe is truly permanent. Even the most stable barriers eventually succumb to quantum effects. Given sufficient time, particles can tunnel through any obstacle, no matter how formidable. This principle implies that the universe itself might one day tunnel into a lower energy state, if fundamentally altering the laws of physics. This paradox reveals the universe's fundamental departure from our intuitive understanding. At quantum scales, solid barriers become permeable boundaries, impossibility transforms into probability, and the very notion of definite location dissolves into mathematical abstraction. Reality operates according to principles where the impossible becomes merely improbable, and barriers exist only as temporary suggestions rather than absolute prohibitions. Delayed choice paradox. Time flows in one direction, carrying cause before effect in an unbroken chain of logic. Yet, quantum mechanics suggests something far more unsettling, that future decisions might reach backward, influencing events that have already occurred. This is the essence of the delayed choice paradox, a puzzle that challenges our most basic assumptions about time and causality. The paradox emerges from variations of the famous double-slit experiment. When a photon encounters two parallel slits, it creates an interference pattern on a distant screen, suggesting the photon somehow passed through both slits simultaneously. But when we place detectors at the slits to determine which path the photon took, the interference pattern vanishes, and the photon behaves like an ordinary particle. The delayed choice version adds a twist that defies comprehension. Scientists can decide whether to measure the photon's path after it has already passed through the slits, but before it reaches the detection screen. Remarkably, this future choice appears to retroactively determine whether the photon exhibited wave or particle properties during its earlier journey. In one striking experiment, researchers used rapidly switching devices to make the detection choice while photons were already in flight. The results consistently showed that the future measurement decision influenced the photon's behavior throughout its entire journey, even during periods when that decision had not yet been made. This paradox becomes even more mind-bending when applied to astronomical scales. Light from distant quasars can be gravitationally lensed by intervening galaxies, creating multiple paths to Earth. By choosing whether to measure which path the light took, astronomers might be influencing events that occurred billions of years ago, when the light began its journey across the cosmos. Some interpretations suggest that reality remains fundamentally indeterminate until observation collapses the quantum wave function. In this view, the past exists in superposition, encompassing all possible histories simultaneously, until future measurements force reality to choose a specific narrative. Alternative explanations propose that information somehow travels backward through time, or that our conventional understanding of temporal sequence breaks down at quantum scales. Perhaps causality itself is more fluid than we imagine, with future and past intertwined in ways that transcend our linear perception of time. The delayed choice paradox forces us to reconsider fundamental questions about the nature of reality. Does the past exist independently of our observations? Can consciousness reach backward through time to influence events? Or does reality exist in a constant state of flux, crystallizing into definite form only when we choose to look? The paradox has practical implications for our understanding of information and computation. If future measurements can influence past events, conventional notions of information flow and processing require fundamental revision. Some theories suggest that quantum computers might exploit these temporal effects to solve problems by reaching backward through time. The phenomenon also raises profound questions about free will and determinism. If our future choices can influence past events, what does this mean for the concept of predetermined outcomes? Perhaps the universe exists in a state of temporal superposition, where multiple timelines coexist until conscious observation selects a specific historical narrative. Recent experiments with delayed choice quantum erasers have pushed these concepts to their limits. Scientists can now manipulate the quantum properties of photons after they have completed their journey, retroactively determining whether they exhibited wave or particle characteristics throughout their entire path. These experiments suggest that the past remains fluid and negotiable far longer than we ever imagined. The delayed choice paradox ultimately challenges us to abandon our linear conception of time. Perhaps past, present, and future are human constructs that break down at fundamental levels of reality. The universe might be far more interconnected across time than space, where every moment influences every other moment in an eternal dance of cause and effect that transcends our ordinary understanding of temporal sequence. Many worlds paradox. Consider a simple choice: taking the left path or the right path through a forest. In our familiar reality, you select one route and continue your journey. But according to the many worlds interpretation of quantum mechanics, both possibilities actually occur. You take the left path in this universe while another version of you simultaneously takes the right path in a parallel reality. This interpretation, proposed by physicist Hugh Everett in 1957, attempts to resolve the measurement problem in quantum mechanics. Traditional quantum theory describes particles existing in superposition, occupying multiple states simultaneously until observed. But what happens during measurement has long puzzled scientists. The many worlds interpretation offers a radical solution. Nothing collapses. Instead, reality branches into multiple parallel universes. Every quantum event spawns countless universes. When a radioactive atom decays, one universe contains the decay event, while another contains the undecayed atom. When a photon encounters a beam splitter, one universe receives the transmitted photon, while another receives the reflected one. Each possibility becomes reality somewhere in the vast multiverse. The mathematics of quantum mechanics naturally leads to this proliferation of worlds. The universal wave function evolves deterministically, never collapsing or disappearing. What we perceive as randomness emerges because we exist within just one branch of an endlessly dividing tree of realities. This interpretation has profound implications. Every decision you make, every quantum event in your brain, every random occurrence in the universe creates new branches. There are universes where dinosaurs never went extinct, where you chose different careers, where the laws of physics vary slightly from our own. The number of parallel worlds grows exponentially with each passing moment. The paradox lies in the theory's untestability. These parallel universes remain forever isolated from our own. We cannot communicate with our alternate selves or visit other branches of reality. The many worlds interpretation explains our observations perfectly while making predictions we can never verify. Some versions suggest that all mathematical possibilities exist as physical realities. This leads to the unsettling conclusion that universes containing every conceivable horror exist alongside worlds of unimaginable beauty. Every story ever written or imagined plays out somewhere in the multiverse. The theory also raises questions about identity and consciousness. Are you the same person as your parallel selves? Do you have moral obligations to alternate versions of yourself and others? If every possible outcome occurs, do your choices actually matter? Critics argue that the interpretation violates Occam's razor by postulating an infinite number of unobservable universes to explain finite observations. Supporters counter that it's the most natural interpretation of quantum mechanics, requiring no additional assumptions about wave function collapse. The interpretation also suggests that consciousness itself might branch along with physical reality. Each version of you experiences only one timeline, creating the illusion of a single, continuous existence. Your memories and experiences represent just one path through an infinite maze of possibilities, while other versions of yourself accumulate entirely different sets of experiences. This raises uncomfortable questions about probability and prediction. If all outcomes occur somewhere in the multiverse, what meaning can we assign to probability? Perhaps quantum mechanics doesn't describe uncertainty, but rather the measure of how many worlds contain each possible outcome. Rare events still occur. They simply happen in fewer branches of reality. The energy requirements for maintaining infinite worlds present another puzzle. Creating new universes with every quantum event should require enormous amounts of energy. Yet, we observe no such drain on our universe's resources. Some theorists propose that the total energy across all branches remains constant, with new worlds borrowing energy that gets repaid through quantum fluctuations. The many worlds interpretation transforms questions about the meaning of existence into questions about the nature of experience. If infinite versions of every possible life unfold across the multiverse, what makes your particular experience special? Perhaps the answer lies not in uniqueness, but in the irreducible reality of consciousness itself. Entanglement Paradox. Two particles, created together in a single quantum event, become forever linked in what Einstein famously called spooky action at a distance. No matter how far apart these particles travel, whether separated by meters or galaxies, measuring one instantaneously affects the other. This quantum entanglement paradox challenges our understanding of locality and the fundamental structure of reality. When particles become entangled, they share a single quantum state, despite existing as separate entities. If one particle spins clockwise, its partner will spin counterclockwise. If one has vertical polarization, the other adopts horizontal polarization. This correlation persists regardless of the spatial separation between them. The paradox emerges because this connection appears to operate faster than light, seemingly violating Einstein's special relativity. When scientists measure an entangled particle in New York, its partner in Tokyo instantly knows the result and adjusts its properties accordingly. No signal travels between them, no communication occurs, yet the correlation remains perfect. Einstein, Boris Podolsky, and Nathan Rosen highlighted this paradox in 1935. Arguing that quantum mechanics must be incomplete. They propose that hidden variables determine each particle's properties from the moment of entanglement, creating the illusion of instant correlation. Local realism, they insisted, demanded that particles possess definite properties independent of observation. Decades later, physicist John Bell developed a mathematical test to distinguish between quantum mechanics and local hidden variable theories. Bell's inequality experiments consistently support quantum mechanics, demonstrating that entangled particles genuinely lack definite properties until measured. The correlations are real, not predetermined. This has profound implications for our understanding of reality. Entangled particles exist in superposition, sharing indefinite properties until observation forces them into definite states. The measurement of one particle doesn't send a signal to its partner. Instead, it resolves the shared quantum state that encompasses both particles simultaneously. Modern experiments have confirmed entanglement across increasingly vast distances. Scientists have entangled particles separated by hundreds of kilometers using satellites to create space-based quantum links. These experiments consistently demonstrate the non-local nature of quantum correlations. The paradox deepens when we consider multiple entangled particles. Groups of particles can share complex quantum states, creating networks of correlation that span arbitrary distances. Disturbing any member of the group instantly affects the entire network, regardless of the spatial arrangement. Quantum entanglement enables revolutionary technologies. Quantum computers harness entangled states to perform calculations impossible for classical systems. Quantum cryptography uses entanglement to create unbreakable communication channels. Quantum teleportation employs entangled pairs to transfer quantum information across space. The phenomenon suggests that information doesn't travel between entangled particles because they never truly separated in the first place. They remain part of a single quantum system, distributed across space but unified at a deeper level of reality. Measuring one particle doesn't send a signal to its partner. It reveals information about the shared state they both inhabit. This has led to new theories about the structure of space-time itself. Some physicists propose that space emerges from quantum entanglement, with distance and separation arising as approximate concepts valid only at macroscopic scales. At the fundamental level, the universe might be a network of quantum correlations with space and time as secondary properties. The Entanglement Paradox also illuminates the role of information in physical processes. Quantum information differs fundamentally from classical information, existing in superposition and exhibiting non-local correlations. This quantum information can be teleported, encrypted, and processed in ways impossible for classical systems, opening new frontiers in communication and computation. Recent experiments have pushed entanglement to cosmic scales, using photons that traveled for millions of years from distant stars. These tests confirm that quantum correlations persist across astronomical distances and vast spans of time, suggesting that the universe itself might be fundamentally entangled. The Entanglement Paradox reveals that space might be less fundamental than we imagine. At quantum scales, separation becomes meaningless for particles sharing common origins. Reality appears to be non-locally connected in ways that transcend our everyday understanding of distance and independence. The cosmos appears to be bound together by invisible threads of quantum correlation that operate beyond the constraints of space and time. Quantum Causality Paradox. Cause precedes effect. This principle forms the bedrock of our understanding of time and reality. A stone thrown into water creates ripples afterward, never before. Yet, quantum mechanics suggests scenarios where effects might precede their causes, creating paradoxes that challenge our most fundamental assumptions about temporal order. The paradox emerges from quantum tunneling, combined with relativity. When particles tunnel through energy barriers, they appear to traverse the barrier instantaneously, or even arrive on the other side before classical particles would. Some interpretations suggest tunneling particles spend negative time within the barrier, effectively arriving before they depart. Recent experiments have measured this phenomenon using sophisticated timing techniques. Researchers found that particles emerging from quantum barriers showed arrival times that preceded what classical physics would predict. The particles seem to experience a form of time travel, spending a negative duration within the barrier itself. This temporal anomaly becomes more pronounced when considering relativistic effects. In scenarios involving high-speed particles and multiple reference frames, the sequence of events can appear different to various observers. What one observer sees as cause and effect, another might witness in reverse order. The paradox extends to quantum field fluctuations, where virtual particle pairs continuously appear and disappear throughout empty space. These fluctuations occur so rapidly that they seem to violate energy conservation, borrowing energy from the quantum vacuum and repaying it before the universe notices. Time itself becomes negotiable at quantum scales. Quantum measurement adds another layer of complexity. The act of observation appears to retroactively determine which properties particles possess before measurement. Future measurements seem to reach backward through time, influencing past events in ways that create closed causal loops. Some theories propose that quantum systems exist in superposition not just across space, but across time, past, present, and future, coexist simultaneously until observation collapses the temporal wave function into a specific sequence. Causality emerges as an approximation valid only at macroscopic scales. The delayed choice quantum eraser experiments demonstrate this temporal flexibility. Researchers can erase or restore interference patterns in ways that seem to change the past behavior of photons. Future decisions about whether to observe path information retroactively influence whether photons behaved as waves or particles during their earlier journey. These paradoxes suggest that time might not flow in the linear fashion we experience. At quantum scales, temporal order becomes fluid, with cause and effect intermingling in patterns that transcend our classical intuitions. The universe seems to operate according to principles where past and future are equally real and equally negotiable. The paradox also challenges our understanding of free will and consciousness. If effects can precede causes, what happens to the notion of choice and decision-making? Some interpretations suggest that consciousness itself operates outside conventional temporal constraints, with awareness spanning multiple moments simultaneously. Our perception of making decisions might be an illusion created by our limited ability to perceive time's true nature. These temporal anomalies might explain other puzzling aspects of quantum mechanics. The apparent randomness of quantum measurements could result from causal loops that create genuinely unpredictable outcomes. Future events might influence past measurements in ways that preserve the appearance of randomness while maintaining underlying determinism. The implications extend to cosmology and the nature of the universe itself. If quantum effects operated during the Big Bang, causal paradoxes might have played a role in determining the fundamental constants and laws of physics. The universe might have literally bootstrapped itself into existence through quantum causal loops that transcend normal temporal logic. Some theories propose that time itself is quantized, existing in discrete units rather than flowing continuously. At these smallest temporal scales, the normal rules of causality might break down, allowing effects to precede causes within individual time quanta, while preserving causality at larger scales. The quantum causality paradox forces us to reconsider fundamental questions about the nature of time itself. Perhaps causality is an emergent property that arises from our limited perspective rather than a fundamental law of nature. The universe might operate according to principles where effects precede causes and time flows in directions we have yet to comprehend. I hope you enjoyed this video. If you're still awake, there's another cosmic journey waiting for you right here on the screen. I think you'll love it. Until next time, stay curious and sleep well.